My name is Ashley Kane, and this is my presentation for Physics 2212 of Lab 2. Charge tapes is lines of charge, and this is an extension of Lab 1. The intention of this lab is to observe interactions between charged pieces of tape to become familiar with physics principles of charge, electric force, and excess charge on a line of charge. Here is the procedure for the physical model for this lab. The first step was to create a charge on a length of tape by pulling it from another piece of tape repeatedly, the second piece of tape being stuck to the table. We would repeat this process to create another piece of charged tape. Then we would create a setup similar to the one below and handle piece A as infrequently as possible. We would move piece A closer to piece B until piece B begins to float, and we would record the distance at which tape B begins to float. Next, here are some necessary physics principles and equations that we needed to know to calculate some values for this lab. First, we have the force due to gravity. Second, we have the electric force, which is equal to charge times the electric field of the source. Then we have the electric field due to a point charge, which is equal to Coulomb's constant times the charge of the point divided by distance squared. Then for lab 1, to find the charge, it was important to know that at the point at which the tape would float, the force of gravity is equal to the electric force. For this lab, it's also important to know the principle of superposition, which is treating the line as being made up of small segments of charge. Each of these small segments we assume to have equal charge and treat them like point charges. Some other assumptions for this lab is that there's no air resistance in this model, there's an even distribution of charge and the same charge on each tape, and the charge is evenly distributed on each segment, and they can be summed up to find the entire charge of the tape. Here's some additional constant information that we gather from the physical model. The length of the tapes are 0.2 meters long. The mass of the tape is 2 times 10 to the negative 4th grams, and the distance between the two for them to float is 0.005 meters. On the right is an FBD of the interacting tapes. The red points represent the superposition of tape B, and the blue points represent the superposition of point A. The yellow arrow downward from tape B is the gravitational force, and the green arrows upwards represent the electric force on tape B. Now I'm going to talk about the computational model created in GlowScript. I began by defining constants, the first being Coulomb's constant, which is 1 over 4 pi epsilon naught equal to 9 times 10 to the 9th. We also have the gravitational constant, the mass of one tape, which was calculated in the previous slide, and the estimated net charge on one piece of tape, which was found in lab 1 to be 2.33 times 10 to the negative 9th coulombs. We also place the position of the top tape and the bottom tape, the top tape being 0.005 meters away from the bottom. Next, we found the magnitude of the electric field as a function, taking in the charged particle and observation location. We used the equation E equals Coulomb's constant times charge divided by distance squared times r hat. This function would return the electric field with the units newtons per coulomb. This section defines each of the tapes and changes them into a series of point charge per the superposition principle. Here's the function to calculate the electric field. This includes a nested for loop, which will iterate through each of the sections of the tape to find the net force on each and update the net force and electric field by summing the individuals from each of the point charges. Here is the output from the GlowScript after running the code. The yellow arrow represents the gravitational force, which is 1.962 times 10 to the negative 3rd newtons. The magnitude of the electric force is the green arrows, and each of the magnitudes of each of the points is 1.998 times 10 to the 4th newtons. However, multiplying that by 10 would mean that the total electric force is 1.998 times 10 to the 3rd newtons. The electric force in the last lab using just the point charge was equal to 1.962 times 10 to the negative 3rd newtons, and this one from the line charge was equal to 1.99 times 10 to the negative 3rd newtons. This difference comes from The summation of point charges that make up the line using the superposition principle instead of just using one point charge like we did in the last lab. Also, this time we took into consideration the x and y components instead of just the y component. Since we took into consideration the x and y components, the representation using the line charge would be more accurate and closer to the real value because it uses the principle of superposition, which is more accurate for the charge and force exerted by charges in a line. So for this reason, the electric field calculated in lab 2 would be more like the real value.